Let's take a minute to talk about bearings. Here are 4 common bearing assemblies that you might find on any given motor or generator. This bearing has cylindrical roller elements and is called a cylindrical roller bearing. You can see that the inner race can be removed from the bearing assembly because this bearing cannot tolerate any axial thrust. But because of the cylindrical elements, it can accommodate a very large radial force. This is especially useful on a belted application, commonly used in a paper mill. The second type of bearing assembly is probably the most common on smaller motors, and that's a ball bearing assembly. This is a deep groove ball bearing assembly, and it's good at resisting radial and axial forces. The third type of bearing assembly, and the one that you'll be exposed to the most, is a sleeve bearing assembly. Here we have 2 smaller sleeve bearing assemblies, which we'll talk about in more detail. Let's take a minute to talk about bearing assemblies. Here we have 2 sleeve bearing assemblies, which are smaller but still very common for the kinds of motors and generators we work on typically. The bearing sleeves are split in half and have dowel pins to align the halves. You can see on one of the sleeve bearing assemblies, we have a phenolic or bakelite insulating feature. Sometimes on newer machines, this will be a Teflon component, or even will be installed on the receiving part within the bearing assembly. But here we've got the insulating feature installed on the sleeve itself. This is designed to prevent stray currents from circulating around the rotor shaft and will typically be installed on one of the sleeves only. You can see on the other bearing sleeve, you just have metal. What we can also see here at the bottom is a location for an RTD, and this bearing is designed to run in either direction, so it's got RTD ports on this side. Here we've got an anti-rotation pin on the top, and this gets captured by the bearing cap so that if some torque is applied to the bearing, the sleeve won't rotate with the shaft. One of the most important things about the bearing sleeve is the babbitt material. So when we look at the bearing, we see that it appears to be all steel, but upon closer inspection, you can see that there's a different material along the inner diameter here. This material is made out of babbitt. Now, babbitt is aluminum and tin mixed together, and these are specifically chosen because they're soft materials. Normally, the shaft will be rolling on a thin film of oil, and no contact occurs. But if we were to lose the oil film, the shaft will run in a hard contact with the bearing. If it was a steel component, the two would fuse together and there would be damage. But because we use this soft alloy, it will melt and protect the bearing shaft, or excuse me, the journal. Now we can see here that this unit has run. The wear pattern on the bottom sleeve is very consistent along the length of the bearing, but interestingly, it's shifted up to one side. So this bearing was not well aligned in the final assembly. Another important feature of the bearing sleeve is this oil pocket. You can see here a small depression has been cut into both sides of the bearing sleeve. This is designed to trap oil and then entrain it as it rounds about the bearing sleeve. This is a location to pay extra attention to when you're inspecting a bearing because contamination or other foreign debris will accumulate here and cause scratching. Before we reassemble a bearing, we want to be impeccable about our cleanliness and make sure and wipe the bearing down with a clean rag so no foreign contamination enters the unit. So this is an area to take several photos of, as well as of the wear pattern at the bottom for your field report. I'd like to explain now the basic operation of a sleeve bearing. Sleeve bearings have been around for centuries and are extremely effective because they don't require any external forced lubrication or electrical connections. So if we take a cross-section of the shaft, and let's say it's rotating clockwise, to support this shaft, we'll draw the lower bearing sleeve, which is shown like so. I've exaggerated the clearance between the shaft and the bearing sleeve, but typically that gap will be somewhere on the order of 0.005, maybe up to 0.010 inches. And that depends on the size and speed of the machine. Now, as I mentioned before, there's a small oil pocket on both sides of that bearing sleeve that help the oil get into the film under this bearing assembly. So the shaft is actually floating on the bearing sleeve, and there's no contact during operation, which is why a sleeve bearing can last for longer than the life of the motor. Now, how do we get oil to that bearing assembly? It would be easy in the large reservoir upon which this is all set to simply give oil right to the level of the shaft. The problem with that arrangement is it would tend to cause foaming of the oil, and we would have oil foam leaking out of the machine. So a clever person a long time ago made a design as shown. We keep a level of oil down here in a reservoir, and then we add a ring, a large brass ring, which is often called a slinger ring. That ring is simply hanging on the shaft, rolls around with the shaft during rotation. Oil is picked up on the ring because the oil sticks to it, and then it's deposited on top of the bearing, on top of the shaft as it rotates. And this oil is then trapped under the sleeve and the system is lubricated. No external lubrication is required, so this is a very robust assembly used for almost all low-speed applications.